This is problem set 3, exercise 3. In this exercise, they're asking us to calculate the expected number of self-loops and multilinks in a configuration model. In order to do that, we are going to use the probabilities that we saw in the classroom. Okay, so remember that this is the probability of a self-loop, of a node with degree ki of having a self-loop, and this is the probability of multiple links between nodes in the network. So first of all, I'm going to calculate the expected number of self-loops, which is just the addition for every node in the network of this probability. So the expected number of self-loops is going to be the addition, okay, from I equal to 1 to n of PII, which is Ki times Ki minus 1 over 2 times 2L minus 1. Now, in order to do this calculation, what I'm going to do is I'm going to assume that the network is large, and therefore instead of writing 2L, okay, all these 2L minus 1, okay, this expression here, 2L minus 1, 2L minus 1, 2L minus 2, I'm going to approximate it by 2L. So that's one thing that I'm going to do in order to solve this more easily. So what I'm going to do is this is going to be approximately the same as the addition Ki times Ki minus 1 divided by 4L. Now, 2L, it's equal to the total number of links, which in an undirected network, because the configuration model usually is defined for an undirected network, and we saw in classroom that it was an undirected network, this is the average degree times the number of nodes. So this is what I'm going to write instead of 2L. And I'm going to expand this expression on the Ki's. So this is the addition from I equal to 1 until n, the summatory of Ki squared minus Ki divided by twice the average degree times n. And now this is the same as 1 over twice the average degree. And this summatory is, when I divide it by n, this is just the average K squared minus the average degree. So this is the result for the first part of the exercise, for the average number of self-loops. Now I'm going to do the same for the expected number of multilinks. So I have to do exactly the same, okay? What I'm going to do, well, now I have to do the addition for every I and every j divided by 2, because I'm counting twice. When I do this summatory, I'm going to count twice every link. So I'm going to do this addition, and this, well, I'm going to rewrite this. I'm going to reorder the factors here. I'm going to write this Ki and Ki minus 1 on the one hand, and this other one here. Okay, so now, so I can do it easier. And remember that I'm going to write 2L squared, and then I'm going to write, instead of 2L, I'm going to write this expression here. So I can separate these two parts. So, well, I'm going to write, this is twice, and then the average degree times n squared, and then the summatory on I of Ki squared minus Ki, and then the other summatory in j of Kj squared minus Kj. Here I just did the following. Since we have a part of this of the terms that only depends on I and another one that only depends on j, this expression is exactly the same as doing this calculation, okay? If you use the distributive property of the sum and the multiplication, this is what you obtain. So in this case, since I have here n squared, I can use one of the n's dividing here and the other one dividing here. And what I'm going to obtain is 1 over 2 twice the average degree times k squared minus, k squared average minus k average, and exactly the same for the other factors, so here I have a squared. So this is the result for the average number of multilinks in the configuration model.